Hey Space Invaders, I got a lot of comments on my previous video asking me to go through a tutorial of a practical astronomy problem using some of the Python packages that I mentioned in that video. I thought a really good introductory tutorial that uses all four of those packages would be to show you guys how to determine the redshift of an object given its observed spectrum. For this tutorial, I'm just going to go through the building and testing of the functions that we'll need to do this task, and then in a later video, I'll show you guys how to actually apply these functions to real data in order to get the redshift of the source. There are a few topics that are involved in this tutorial. I'm not going to go over them here, but those include knowing about least squares fitting, the functional form of a Gaussian, the Doppler redshift equation, and just knowing what a spectrum is in general. I'm also going to assume that if you're following along with this tutorial that you have some familiarity with Python and with Python notebooks. I can do some very simple tasks in Python. If you're not familiar, maybe go to my previous video and click some of the links in the description section to help get you started on being comfortable with Python. Okay, so just to be clear, the goal of this tutorial is to teach you guys how to determine the redshift of a galaxy given its observed spectrum by fitting a Gaussian profile to the emission line features in the observed spectrum and backing out what the shifted line center of those emission line features is. Then we'll compare those shifted line centers to the expected rest frame line centers when the galaxy emitted those emission lines to determine the redshift of that galaxy. So let's open up a new Python notebook. And the first step is to import all of the necessary packages. But before we do that, let's actually name this notebook something. So I'm just going to call it functions least square fit spectrum. You can call it whatever you want. Okay, so let's import some packages. The first one that we're going to need is the NumPy package. Like I mentioned in my previous video, this package gives you a lot of array functionality, and it has some useful functions like exponentials and square roots that will help us build our Gaussian model that we're going to fit to the emission lines. So we're going to import numpy as np, and this as np is just importing the NumPy package and then putting it under the np variable so that we don't have to call or type out NumPy every time we want to use an np function. The other package that we're going to need is the matplotlib library. This is a plotting library, and so we're going to import matplotlib.pyplot, which is the plotting package, but we're going to import it as plt so that we don't have to type out matplotlib.pyplot blah, 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 every time we want to use that package. Okay, so if you're in Jupyter Notebook, you're going to want to do a Shift Enter to execute that cell and import those two packages. Okay, so the next step is to define the functions that we're going to need. So for each function, we'll want to perform a simple test to make sure that our function is working properly. So we're performing a least squares fit between some input data and a model. And in this case, in the case of emission lines, our model is going to be a Gaussian profile. So we're going to need a function that returns a Gaussian. So let me go ahead and give you guys the equation for a Gaussian. I'm just going to paste this here because it would take too long to write out. So I'm going to convert this cell to Markdown, which just lets you type regular text and latex text into Jupyter Notebook. And so this is our Gaussian equation. So we need to write a function that basically creates this. So to define a function, we're going to do def and then the name of the function. Let's call it Gauss. And for Gauss, we want to pass it an X array that the Gaussian is going to span. So we'll pass it X. We also want to pass it an amplitude, and then the line center or the mean of the Gaussian, as well as the sigma, which describes the width of the Gaussian profile. For each function we make, we also want to include a docstring because this is just good practice. I always forget to do these, but it's a way to describe what your function's doing so that if someone else tries to use it, they don't have to sit there and try and figure out what's going on. And so we're just going to say that this function returns a Gaussian profile. Okay, and so our Gaussian, let's just call it the variable Gaussian, is going to be A divided by, and it looks like there's sigma times, and this is where numpy comes in. We're going to do np dot square root of 2 times, and then we can also do np dot pi to get the pi symbol. Okay, and then that whole thing is going to be multiplied by np.exp, which gives us our exponential. And the argument of the exponential is going to be negative. Pow is just a way, it's a built-in function in Python, and it allows you to take the power of some argument. So in this case, we're doing x minus the mean squared. And then we want to divide pow by 2 times sigma squared. So pow sig to the 2. And let's make sure all these parentheses are correct. I think it looks good. Okay, and then we want our function to return this Gaussian variable. Okay, so shift enter to execute that. So let's test this function real quick. So first we're going to need to pass it an array of x values. So let's do x test. And I'm just going to make this an array of values in between 0 and 20. And this linspace, numpy linspace, just basically gives you an array of values between two numbers that you specify. And then you tell it how many of those numbers you want, and it'll linearly space those. So it'll be evenly spaced between 0 and 20. Okay, and then we want to test our Gaussian function. So we're going to do Gauss test. And we're just going to call our Gaussian and pass it x test. And then we also need to pass it an amplitude. Let's just give it an amplitude of 1. And let's make sure that the line center is at 5. And then we'll give it a width of 1 as well. And we want to plot that to make sure that it actually produces a Gaussian profile. So let's do plt.plot x test and then Gauss test. And you can autofill variables in the Jupyter Notebook. So I can start typing Gauss test and just press tab and it'll autofill the rest of that variable. Or if there's multiple variables that start with Gauss, it'll give you a list of the variables that start with Gauss and you can click which one instead of having to type it all out. Okay, so we can do plt.show to make it display our plot. And let's see if this works. Cool, looks good. That's a Gaussian profile centered on 5, an amplitude of 1, and a width of 1. Awesome. Okay, so the actual spectrum that we are going to be fitting will have more than just one emission line, and we want to use at least 2 of those to constrain our fit. So let's write another function that is going to combine 2 Gaussians at different line centers into one simulated spectrum. So we're going to start by defining the function. In this case, let's just call it nonlinear func real. And so the nonlinear func is just referencing the fact that this is a least squares nonlinear fit because some of the parameters that we're fitting are in the exponential as opposed to being in a linear function. Okay, so for this function, we want it to combine 2 Gaussians. So it's going to need all of the variables that Gauss needs, but for 2 different Gaussians. So we'll pass it the x values, the x array, just call that x vals, and then we'll need to pass it the amplitude of the first line, amplitude of the second line, the line center of the first line, and line center of the second line. It'll also need a width. I'm going to make it so that both lines have the same width, so I'll just pass it 1 width, w1. And then instead of having a Gaussian that's protruding from a 0 level continuum, we want to give our nonlinear func some continuum level that we set. So I'm just going to put in continuum as a variable that we want to fit. Okay, and so this function combines 2 Gaussians into one simulated model spectrum. So that's our doc string. And so we can just go ahead and return, what we're going to return is the first Gaussian with the x vals as the wavelength axis, the first amplitude, the first line center, and the width. But then we want to also add a second Gaussian that spans the same range of x values, but has the second amplitude, second line center, and the same width. And then lastly, we want to add a continuum level to these Gaussians. And so this should return basically two of these Gaussians together. So we'll execute that cell, and then let's test this. So again, we need to give it an array of x values. So let's give it x test2. And I'll just give it the same range of values between 0 and 20 with 100 different values. And then our y value test is going to be nonlinear func, and you can also tab complete function names, which is cool. And so we'll pass nonlinear func x test2. And this is what I meant when I said if you tab and there's multiple things that start with whatever you've typed, it'll give you options. So x test2, and we need amplitudes for both lines, line centers, widths, and a continuum. So let's give the first line an amplitude of 1, the second line an amplitude of 2. And the first line center we'll put at 5, and then the second one we'll put at 10. And then we'll give it a width of 1 like we did before. And for the continuum, let's just set it at 0.25. Okay, and then let's plot this to test and make sure that it's doing what it's supposed to and creating two Gaussians together. So y val test, tlt.show, and shift enter. Cool. And so that is our double Gaussian, and centered at 5 and 10. This amplitude is twice the height of the first one, which is what we had specified. So I think that looks pretty good. Okay, so now we need a function that's going to take this nonlinear func model and fit it to some input data. The SciPy package has a function called curveFit, which we're going to be using. So I guess that's something that I forgot to read in. So let's go back up and do that. We're going to need the SciPy optimized curveFit. So we're going to say from scipy.optimize import curveFit. Okay, and that's going to be what we'll use to fit our nonlinear func real model to our data in the next video. But we're going to want to test it out, so we'll need curveFit for this video as well. Okay, so curveFit is really easy to use. You basically pass it the name of the function that you want to use as your model. You pass it the x and y values for your data. You can optionally pass it the error on your data values, your y data values. And then you also need to give it initial guesses for each of the parameters that you're trying to fit. Okay, so curveFit, once you provide it with all of that, will return two things. It will return the best fitting parameters between your model and your data, and it'll return a covariance matrix, which gives you the variance on your best fitting parameters and the variance or covariance between the parameters. And so the actual one standard deviation errors on your parameters are going to be the square root of the diagonal components of that covariance matrix. And so I'll show you how we extract that. So let's define a function called fitData that is going to fit our nonlinear func model to some input data that we give it. So fitData is going to need a few things. We want to give it our x and y values, so the wavelengths and the spectrum flux values. We want to give it the amplitude for the first line, the amplitude for the second line, the mean for the first line or line center, the line center for the second line, the width, and the continuum. And I am going to not provide curveFit with the data errors, just because I want to keep this as a pretty simple tutorial. But you can check out the curveFit documentation page if you're interested in how you include that. Okay, so we want this function to do a few things. First, we want it to try and fit the model to our data, but we also want it to print out the results of that fit. So we want it to print out what each of the best fitting parameter values is. And then lastly, we want it to plot the best fitting model along with our data so that we can visually inspect the fit that just occurred. So let's give this a doc string, and it's going to basically fits two Gaussian profiles to a spectrum to determine the amplitudes, line centers, widths, and continuum levels of the spectrum. I should say of the input spectrum. Okay. So, first thing we're going to do is just perform the fit. Something I really like to do, because I just think that it makes things print out really nicely, is to add lines like this, just to keep different sections of this function separated nicely. So I'll do that, and then I'll say that we are we are performing a least squares fit. So I just wanted to I want the function to print out what it's doing. And so remember that there are two outputs from curveFit. The first one is the best fitting parameters, which I'm going to call pop_t, and the second one is the covariance matrix, which I'll call pcov. Okay, and then we can just go ahead and directly call curveFit. We need to pass it the name of the function that represents our model. So in this case, it's nonlinear funcreal. We need to pass it the x and y values for our data, which are wave and spec. And then it also wants you to pass it initial guesses for the model parameters, and it expects those to be in a list whose variable name is p0. So that's going to be amp1, amp2, m1, m2, sig, I called it w1, and continuum. Okay, so that should return the best fitting parameters and their errors, or their variances. To get the errors, like I said, it's going to be the np.square root of the np.diagonal components of the covariance matrix. Okay, and I'm going to copy and paste this nice little horizontal line down here to separate that from the next thing, which is going to be printing out the best fitting parameters and 1 standard deviation errors. Okay, and so instead of having you guys sit here and watch me format how I would want to print this out, I'm just going to copy and paste what I usually do, and you guys can pretty much print it out however works best for you. But I'll just talk about this real quick. So I have it print out each of these parameters, Python arrays and lists index starting at 0. So the first parameter that we fit would be the pop_t 0 component, and then 1, 2, 3, 4, 5. So we're fitting 6 components, but they index up to 5. And so this first one, I'm just printing out the best fitting amplitude for line 1, the best fitting amplitude for line 2, the line centers, and the line width, and the continuum level. And then I also add the errors as part of this printout, just so I can see how well the fit is. And then at the end, I add this new line command, just so these things aren't printed all in the same line, they're printed one on top of each other. Okay, so the other thing, after printing out our results that we want our function to do, is to display the model, the best fitting model, along with our data so we can visually inspect the two. To do this, curveFit only returns the best fitting parameters. It doesn't actually return the model. So we need to take these best fitting parameters and reinsert them into our model in order to get a model curve. So I'll just say that I am plotting the observed and modeled data. Oh. And to do that, I need to create the model, which is just going to be, I'm going to call our model function nonlinear func real and pass it the wavelength array, so wave, but I'm also going to pass it the best fitting parameters. So to do that, I'm going to take pop t and use this asterisk at the beginning of it to unpack each of those values into the nonlinear function call. So this asterisk basically just unpacks those values so that they're not in an array format, they're in this like tuple format. Tuple? Okay, so now we can go ahead and plot our model and observed data. So we're going to do plt.plot, and we want to plot against the wave axis, and we're going to plot the spectrum. And so the label for this data set is going to be data. We're also going to plot the model, again, against the wave axis, and this time it's the Y model array, and the label is going to be model. Another thing that I like to do when I'm fitting emission lines is to put a vertical line where the best fitting line center is, just to make sure so I can visually inspect that parameter specifically. So to do this, we can use the plt vlines function call. So plt.vlines, and we want these vertical lines to be at the line 1 and line 2 wave centers. And so vlines, this first one is going to be at line 1's wave center, and it's going to extend from ymin equals 0 to ymax equals, and I want the maximum value of this line to be the maximum value of our spectrum. And so since spec is an array, we can do spec.max with these parentheses, and it'll give you the max value from that array. I also want to make the line styles dashed lines instead of a solid line, and I don't want it to be like a super bold solid line, so I'm going to change the transparency with the alpha parameter to 0.75, and then lastly I'm going to make sure that the line width is 1 so that it's not too thick. And then I'm just going to copy this because we're basically doing the same thing for the second line, just changing this to 3. Okay, and then we also, since we have labels for each of these data sets, and since we're plotting more than one data set on the same plot, in order for those to show up in a legend is we have to call plt.legend, plt.legend, parentheses, so that'll make sure that there's a legend on our plot. And then again, lastly, plt.show. Okay, and then the last thing this function should do is return those best fitting parameters and the covariance matrix. Okay, so I think that's everything that we need for that function. So I'm going to execute that cell so that our function is defined, and then we're going to test it. So let's test this real quick. We need to give it a wavelength axis, so wave test is what I'll call that. And I'll just make it the same 0 to 20 array with 100 values. Okay, and so we also need to so in order to test this, it would be super easy for us to try and create a model like this one, and then have fit data try and fit a model to that model, if that makes sense. But that's not realistic. So a more realistic thing to do is to use this nonlinear func real function to create a model, and then add some noise to that model so that it's more realistic. And then when we try and use fit data to fit a model to that simulated noisy spectrum, it's a more realistic task for fit data. So it's a better test of if fit data can actually fit the model to that simulated spectrum. So first, let's define our pure model. This is just going to be our nonlinear func real model function. We're going to pass it wave test, and then we're going to pass it the different parameters. So let's since we're going to add noise to this fake data set, we want to use amplitudes that are high enough so that when we add the noise, the amplitudes aren't buried in the data, the fake data. So I'll just show you what I mean by that. Using the same variables or parameters that we used before, if I do this and then I do func test, I don't know, func test, I guess we'll just call it that. We're basically going to take our pure model and we're going to add random noise using the numpy.random.normal function. And so this is basically going to add a random value drawn from a normal distribution which is centered on pure model and add that random value to pure model. So we're basically adding noise to each flux value at each wavelength in this simulated data set. So the location is going to be centered on the pure model values, and we want the size of this array of random values to be equal to the size of pure model so that they can actually be added together. Okay, so let's just plot this, and I'll show you what I mean by if the amplitudes aren't big enough, then the noise is just going to bury the signal from the amplitudes. So wave test and then func test. Okay, and we'll just plt.show that. And there you go. You see, like, there's a small bump there, maybe one there, but the noise has just drowned it out. So instead of that, let's change these amplitudes to, we'll say 20 and 40 for the amplitudes. I think those are pretty good. And we'll still keep them centered at 5 and 10, widths of 1 and a continuum of 0.25. And let's see what that does. Cool, so that's much better. I think that'll be a lot easier for us to fit. And it also gives us a pretty realistic view of what a spectrum would look like, or somewhat realistic. Okay, so let's try and fit this simulated data set that we just created. So again, our fit data function is going to have two outputs that it returns. These are going to be out t, the best fitting parameters, and out eco. And we're going to call fit data. And again, remember that we need to give it our wavelength, so wave test. And we need to give it our spectrum, which we called func test. And then we'll also need to give it initial guesses for each of these parameters. So let's just try and read these parameters off of this plot that we just made and see if what we can read by eye is close enough to help it fit the data. So the first one is the first amplitude, which looks like it's about at like 18. So let's say 18. The second one is about 32, 33. The first one is centered at like 5-ish. I'm gonna guess that it's centered at 4.5 just to see if I can trick the fitting function. And I'll say the other one's at 9.5. And then the width, let's say that the width is 1.5, and I'll give it a continuum level of 0.5 and see if it can figure out what the right continuum level is. Okay, so let's execute this and see if it fits our simulated data well. Okay, so from the plot that it created, it looks like a pretty good fit, but it does look like it's off by a factor of 2 with the amplitudes. But I think this is just telling us that a Gaussian with those amplitudes would also be a good fit to the data, even though we gave it these as the input amplitudes. Okay, it also did pretty well with the line centers, I think, 4.9 and 9.9. I think that's close enough to 5 and 10. And then the line width, 0.98, which is pretty close to the 1 that we gave it. And then the continuum level, it's a little off on the continuum level, but it has a pretty high error on the continuum level anyways, so I think it did pretty well. Cool. And so the last function that we'll need is the one that calculates the redshift of our source spectrum. So the equation for the redshift, I'm just going to go ahead and paste it in here instead of typing it out, even though it's pretty short. So again, I'll turn this cell into Markdown and then print that. So this is the equation for the redshift given a galaxy's observed emission line and the location of the emission line in the rest frame of the galaxy. So it's observed wavelength minus emitted wavelength divided by emitted wavelength. Okay, so we need to define a function that basically just returns this redshift given these input wavelengths. So I'm going to call this function getRedshift, and it's going to have two parameters, lam_o and lam_e, and the doc string. This is basically going to return the redshift of a source given the observed and rest frame wavelengths. Okay, and then we can just go ahead and return that. It's a pretty simple function. It's going to be lam_o minus lam_e divided by lam_e. Okay, and so to test this one, we know that if a galaxy emits a photon at a certain wavelength and we observe the photon at that same wavelength, then that galaxy should be pretty local to where we are, and we should get that it's at a redshift of 0. So if we test this out and we say get redshift, if we give it two of the very same wavelengths, we should get that the redshift is 0. And let's see if we do. And we do. Awesome. Okay. And that's basically the last test and the last function that we need. So now that we know that all of our functions work together, this is great. We can use these to fit an actual spectrum and get the redshift of the galaxy that created that spectrum. That's all I really wanted to share with you guys today. If you have any questions about this stuff, make sure to let me know in the comment section, and thank you everyone for watching.